Hello everybody! I hope everyone's having a wonderful day. So today I'm going to be giving you a research talk. This is going to be based off a talk I gave July 22nd for the Department of Computer Science at Memorial University. The title of this talk is Approximation Algorithms for Makespan Minimization on Unrelated Parallel Machines. So this talk is going to consist of really 4 parts. The first part, I'll tell you a little bit about the kind of research I'm interested in, what gets me excited when I wake up in the morning, when I want to discover more things about the nature of computation. Second, I'll be moving into talking a little bit about approximation algorithms, which I have an interest in. And third, I'll start moving into talking a bit more about a problem that is of what I've been looking at for a number of years now. And then I'll be winding this up with a generalization I've looked at more recently and some open problems associated with that. Anyways, so let's get started. So first, before anything, I am a theoretical computer scientist. I'm interested in the theory of algorithms. So if you were to try to pigeonhole me into 2 areas that you'd say, hey, look, that's what Dan's interested in, it would most certainly be approximation algorithms and combinatorial optimization. So I'm interested in particular in problems that relate to scheduling and packing problems, in particular scheduling primarily, but also graph theoretic problems. So if they tend to have the flavor of both of these, those are ones I find especially fascinating. So if it has a graph, it involves scheduling, I tend to get pretty excited about it. So that being said, in this talk, I'm going to highlight some things from some of my work in about the last half-decade. I'll touch on a few things that I've been working on. So in particular, I'll be talking about so-called graph balancing, unrelated parallel machine scheduling, which is a classic problem in combinatorial optimization. And I'll be talking about and highlighting a more recently studied problem called parallel machine scheduling with bag constraints. Okay, so you might ask, Dan, where are we going to start here? Well, I'm going to start off at one that many computer scientists are interested in, and they approach it with very different approaches. Mine is more of a theoretical computer scientist's approach, so I'm building mine mostly in the theory of computation and modern theories that we currently have about algorithms. But there's many ways you could tackle this general question. The question is, given a hard optimization problem, what we call an NP hard optimization problem, how do you exactly design algorithms for these that are efficient? Or just generally, how do you reconcile intractability, the process of having a problem that is difficult to solve? When I mean solve, I mean by efficiency standards. So these are problems that you can indeed actually solve, just they're going to take a long time to solve if you wanted to try to solve them. That's a lot of me saying to solve, but my point is quite simple. Under complexity theoretic assumptions like p is not equal to np, exact polynomial time algorithms do not actually exist for so-called NP hard optimization problems. So what exactly do we do? And I rely oftentimes on this common phrase. It's fast, cheap, reliable. Pick any 2. So you may have encountered this phrase when talking about like cars or just generally daily life activities where, for instance, there is a trade-off. Trade-offs very often occur when we talk about policies, algorithms. Generally, when you're measuring efficiency, you oftentimes will have trade-offs. So in this aspect, I'm going to be taking and interpreting this in the following way. I'm going to be assuming fast as it runs efficiently in the worst case. So I'm going to say efficient meaning polynomial time. When I mean cheap, I mean that not necessarily that like it has to be the case. So if I'm saying an optimization problems actually have the following structure to them. So if I give you a problem, problems consist of, so if I give you a problem, I call it pi. That's not a number, it's just a symbol. If I give you problem pi consists of problem instances. And when we exactly solve a problem, what we do is we try to solve each one of these problem instances, and if we can solve all of them, we say that we've solved pi. So in an optimization problem, each one of these dots I have in this, there's potentially an infinite number of these. Each one of these will have a set of feasible solutions. So these are ones that follow the constraints or rules of your optimization problem. And some of them in here are going to have the smallest or largest possible value if you evaluated how good the answers were. These are the largest or smallest, depending if we're talking about a minimization or maximization problem respectively. These are called optimal solutions. So the value of them is called the optimum. And generally when we study optimization problems in the exact sense, we like to solve and try to get these optimal solutions. That is generally the goal when we try to solve optimization problems. So that being said, what we want to do is we always want to have it so it computes an optimal solution. Thirdly, we would like our algorithms to actually solve the entirety of a problem. There's two ways you can interpret reliable in this sense. One is that it sometimes works, sometimes it doesn't work. That might be something more applicable to something more like a heuristic, more broadly. These are algorithms that typically cut corners here or there, or sometimes are based on a complicated idea that sometimes allows you to solve something a little faster, but we don't know exactly how well they perform other than by experiment. It's a broad family. Sometimes there's more specialized cases where there actually is more things we know. So the other sense of reliable, I mean, I'm talking about, say if I have a broader problem, I may consider only special ones of these dots called special cases. So maybe only some of these have a special property. Maybe I may consider some of them and I might specialize the instances by so-called parameterizing that problem. I'll talk more about that in a moment. The big point here is that we would like to drop one of those three constraints minimally. That's what a lot of theoretical computer scientists that study algorithms try to do these days, to better understand the underlying complexity of said issues. So when it comes to my interest, I'm generally interested in the interplay between granular theories of algorithms. So there's kind of three worlds for which you can interpret complexity when it comes to solving problems. The first one, most computer scientists in general, many practitioners are familiar with the first world, is the exact computational world. So if we're trying to solve hard optimization problems, the NP hard ones, the best known algorithms typically take exponential time. So normally if you want exact, as in like, yeah, those are the best you're gonna get these optimal solutions always, they're gonna probably take exponential time, assuming that p is not equal to np, that these algorithms are only gonna be like the best ones you're gonna have. Most of the case what we're talking about here. So that being said, that's one way you can interpret things. It's a very powerful and intuitive way of approaching things. The second one, this is the one I'm most interested in, is where we have so-called approximation algorithms. So instead of having it where we always want to get one of these optimal solutions, instead what I would like to do is I would like to compute answers efficiently in polynomial time, but I'm going to sacrifice the quality of the answers by a little bit. This little bit might be a lot, depending on how bad the approximation can be. But the distinction here between a heuristic, more broadly, and an approximation algorithm is that I can actually prove to you how far away my little leniency of how bad it could be actually is. I'll define what I mean by this in a moment. So the third one, and this is the one that I have a growing interest in, is parameterize your fine-grained complexity. So classic computational complexity theory can be thought of as a univariate computational complexity theory. So what do I mean by that? Normally, computer scientists and those interested in algorithms measure the running times of algorithms with respect to the input size of a problem. Why? Because the algorithm scales with the size of the initial input. I won't necessarily go into more detail about that. I have all sorts of fun videos about these sorts of things over on my YouTube channel if you want to learn a little bit more about that. But my point here is that that's univariate. It's over one parameter involving a problem, the running time with respect to the input size. So what happens if you can take more than one parameter about your problem, not just the input size, but maybe something aspect about your problem. Sometimes in practice, it isn't just that, oh yeah, no, it has an arbitrary structure and it's my general problem more broadly. It actually might be that it actually has some special structure to it. Or there might be some intrinsic characteristic of your problem that actually is reflected in the real world. That maybe isn't really well accounted by general cases. So what we would do in these cases, we would parameterize the problem given a parameter, or even more than one parameter, with respect to the input size and said parameter. So a good example of this, if you're familiar with the problem called vertex cover. Vertex cover is an NP-hard optimization problem. And the best known algorithms for these, they take exponential time. So you might ask, Dan, how exactly can we use this parameterized complexity business to talk about this? Well, let me just do it by illustrating just with a very basic example. So imagine you want to think about vertex cover as like an art gallery problem where you have a whole bunch of corners or hallway intersections at an art gallery, and your job is to place security cameras in said art gallery. And you're given the idea that you need to place the security cameras such that you can view every single one of the sweeping hallways in the entire art gallery. And you're tasked with the job of figuring out how many cameras you're going to need and where they should go. So you want to minimize the number of cameras you need because these are very expensive. So this is a very natural application of vertex cover. Now, in real world scenarios, you're not going to, it might be the case that the number of security cameras you actually know maybe even in advance. Or you may have a bound of how many. Who knows, there could be like only like 8 security cameras, not like 200 or something in a big graph. We don't know. But the point is that you might know. So if you know that the vertex cover size, that's what the number of security cameras is, if it exists, so-called this vertex cover, if that is indeed the case, you actually can, if you know that it's small or constant, in particular constant, then what you can actually do is you can solve vertex cover actually in linear time. And the way you actually do it actually is quite similar to an exact approach, but you're given more information to do it, and it actually reflects a thing that a person in the heuristics community might try doing. What you do is you would actually use a bounded search tree approach, or what you do is you decide whether you're going to put a vertex into the vertex cover or not in the vertex cover. But what you're going to do is you're going to cap off this bounded search tree, that's what the technique's called, to the size of the vertex cover. So I'm not going to go into those details here. Just the point here is that by specializing and knowing things about the problem you're looking at, by discovering so-called natural parameters to your problem, so these don't necessarily have to be related to just a given application. It's just that it could have a structural property that can help us better understand the problem than otherwise. So I like to see what's going on between these 3 interpretations of complexity theory. That's generally where I sit. So I'm mostly biased towards approximation algorithms, but I think all 3 of these tend to inform each other, and a lot of the literature these days tends to kind of converge around these 3, where sometimes theory from one informs another, or sometimes when you combine 2 of these approaches, you end up getting something else. For example, I can quote, say, somebody like Daniel Marks, and I remember reading some papers from him, just simply talking about how, I can't remember the exact quote off the top of my head, but if I were to quote him, he would say that that if you take approximation algorithms and parameterized complexity together, you can actually figure out and discover new things that you would otherwise not be able to with each field separately. That's why I think it's important to kind of pick up some of these ideas and see where they actually unify with each other. I do think that there's a unification with some of the language that's used in some of these areas. But the point is that we have everything from exact to so-called fixed parameter tractable algorithms to approximation algorithms. So I'm generally interested in underlying computational complexity issues around these and the design of algorithms. So other than that, obviously because you're here, I'm interested in theoretical computer science pedagogy. I'm interested in getting people excited about theory. So hopefully I'm doing an all right job at that. So anyways, that being said, we're going to talk about what an approximation algorithm is. So before anything, I've actually defined a couple of things on the board here that I've done already. So let's actually lay out a couple of quick definitions. So I want you to imagine I actually have an algorithm. So imagine I have some algorithm. And remember, I have one of my problems here. Imagine I have a problem. I pluck off one of these, and it has input. So I have some inputs. So it has some input. I feed that to the algorithm. Then the algorithm produces one of these dots over here, so-called feasible solutions. So it produces one of these. One of these has a value. We're going to call that alg I, like this. Similarly, there's going to be another value. It's for these guys right here, the optimum. The optimal solutions has a value called the optimum. We're going to call that opt I, where I here is a problem instance. So one of these would be called I. So each one of these is an input instance. So those are my two definitions that I really need to describe what an approximation algorithm is. And it's really quite simple. So what we're going to require for approximation algorithms, so I'm going to define approximation algorithms in this way, is that for every one of the problem instances, the ones over here for my problem, for each one it has to be able to produce me a feasible solution, one of these dots over here. So I feed it to the algorithm spits out one of these at me. It returns that or outputs it. It has to return me one of those in polynomial time. That requirement is very important. It has to be done efficiently. And here's the other part, is that alg I, so this is the value of one of these feasible solutions, it cannot be that much farther away from the optimum. So I'm going to be talking about minimization problems for this talk, so I'm just going to talk about it with respect to minimization. So minimization means that the optimum is going to be as small as possible. So here, if I give you an algorithm, it's going to always produce answers within a multiple of k close to the optimal. So it's going to be a multiplicative constant on opt. So sometimes you're going to find that I'm going to contract opt I to just be called opt later on. So just get used to that. So for example, if k were 2, we'd call this a 2 approximation algorithm, and it would always produce answers no worse than twice as bad as the optimal. So it's about how close it is to the optimal solution multiplicatively. So this k is called an approximation ratio or approximation factor. So that being said, hopefully the idea is quite intuitive. I'm going to actually show you an example, and this should help us lead into some of the talk we're going to have in a moment. So let's do that. So just as a side remark, and this is going to be relevant later, so I need to define something called a PTAS. It's called a polynomial time approximation scheme. So a family is a fancy way of saying, oh, I have a set and all of them are going to be of the same type. So a family is going to be a set of a whole bunch of these algorithms. They're all going to be approximation algorithms. And I'm going to have an approximation algorithm for each rational number that's positive. So just remember rational, those are like your fractional numbers. So like 1/2, 3/4, 0.01. These are your fractional numbers. So for each one of the values of epsilon, there's going to be a 1 plus epsilon approximation algorithm. So you can think of it like a big collection, a family, of approximation algorithms. Now you might ask, Dan, why would I care about that? Well, it's quite simple. If you think about it, if I have a whole family of approximation algorithms, I get to select what epsilon is when I want to actually use this thing. Because it's not just one approximation algorithm, it's a whole scheme of them. It's the whole family of them. So I can think of epsilon like a dial that I can turn. So the closer I can turn epsilon to 0, the better and better my answers are going to get. So for example, if I have epsilon is assigned to be 0.01, I can get within 1% of the optimal solution. And keep in mind, when we're talking about hard optimization problems, such as the ones we're going to be talking about, within 1%, it's pretty darn close to optimal. So it's not like that's terrible or anything. But there's a bit of a trade-off, naturally, is that the closer and closer you get to the optimum, typically your PTAS is going to have a running time that's going to get slower and slower and slower. So, for example, it's very possible for the running time to have something like 1 over epsilon in the exponent. So a PTAS can have something such as like n to the 1 over epsilon as its exponent for the running time. So it can be like big O of 1 over epsilon. So raised to the 1 over epsilon. So if epsilon gets like really small, that exponent's going to get very big, and that'll become very slow. So PTASes are allowed to do things like that. However, there are special kinds of PTASes, such as fully polynomial time approximation schemes, that they forbid you from writing things like this in the exponent. There has to be polynomial both in the input size and 1 over epsilon. So some problems have FPTASes, fully polynomial time approximation schemes. Some don't, assuming that P is not equal to NP. Okay? So naturally, if you think about it, instead of thinking about a big family as we're going towards 0 or we're changing the value, if you pick a particular epsilon and you fix it, that means that there is actually a polynomial time approximation algorithm here. So it's going to take polynomial time. It's a polynomial time algorithm. It guarantees that quality of solution. That's the most important thing I need you to take from this. So I'm going to illustrate the idea of an approximation algorithm with the so-called multiprocessor scheduling. So this is going to be kind of like the toy example, but it's still a fundamentally important scheduling problem. I need to really stress that this is a fundamental problem in scheduling. So we're going to be talking about what scheduling theorists would call Makespan minimization on identical parallel machines. In scheduling theoretic notation, we would call it Cmax. Now, just because I feel like doing so, I'm going to explain a little bit about scheduling theoretic notation. So this is sometimes called Graham's notation. Other times it's called three-field notation. Either way, there's 3 fields that are associated. You have a machine environment, you have conditions. So these are restrictions you could be placing on the problem, or there's special conditions the problem has. And then you have an objective. So you might have more than one of these. But the point here is that the 3 fields, machine environment, job characteristics, and this is your optimality condition. So in our case, we're going to have P Cmax. So Cmax is going to mean something we're going to call the makespan. And that's going to be the central objective in all the problems we're going to talk about today. So P means identical. I'm going to tell you what identical means in a moment. But there's 2 other machine environments I do want you to be aware of, is Q and R. So this Q means uniform. I didn't create these symbols, so don't ask me why they need to be like this. So P I usually think is parallel, Q as like quotient, because I like to think of it as quotient, but I don't necessarily know if that's the reason why. And R is going to be unrelated. That's going to be the one we're going to primarily focus on towards in a moment. Uniform is where the machines have different speeds. So the length the job takes to process depends on the speed of a machine. This one, we're going to assume that the machines are purely homogeneous, meaning they have the exact same speeds. And in unrelated, this is the most general case. This is where we're going to have it where the machines and jobs have no relationship with one another when it comes to the processing. Okay? So, anyways, let's move back over here. So, when we talk about this problem, we're going to have a set J of n jobs, and we're going to have m parallel machines. Now, parallel machines, as the name would suggest, is all the machines execute in parallel. So what happens is you have a set of jobs. Each job has to be assigned to a machine. And once you process the actual schedule that we're trying to produce, each one of the jobs has to, once it starts, it gets continued execution until its completion. It cannot be paused. It cannot be migrated to another machine. So you got to think of these tasks like they're really important, or there's something that once you start them, you have to finish them. So when we talk about a parallel machine like this, all the jobs execute independently on each of their machines because they operate in parallel, right? So what do you think the objective is here? What we're going to do is we're going to try to produce schedules where the length, the total time it takes to complete all the jobs is as small as possible. And we call that the Makespan. Okay, so that's our optimization problem we're going to look at. So at least for this example. So assuming that P is not equal to NP, you're not going to find efficient exact algorithms for this problem. So that's the bad news. The good news is that there actually are nice and efficient approximation algorithms for this problem. In fact, there's still people that do study approximation algorithms for this problem, even though it's been studied for decades. People study PTASs, for example, for this problem and try to improve the running times over other ones. I think there was a paper published not that long ago actually improved on the best known running time of a PTAS. So just before I get too heavy on things, I just want to do a very basic example. So imagine I have 5 jobs here, and I'm going to place them into something called a Gantt chart. So those that do more management related things, you might know of what a Gantt chart is. You have a timeline, and I'm going to have rows for my agents or machines. I must stress, we're talking about scheduling theoretic conceptions of machines and jobs. These don't have to be jobs like computer jobs. They don't have to be machines like processors. They can actually be agents like people, and the task could be things like tasks you have a person do in their daily life. So this is you could consider this a broad scheduling theoretic model. So I have 5 jobs here, and my job is to assign each one of these jobs to a machine. So I have to assign it to a row. So just to give you an example, here's an assignment of all the jobs to machines. And let's see what I got here. So I have the schedule with Makespan 5. The reason why it's 5 is notice that if you look along the horizontal axis, that you end up with, if you count up the ticks, you have 5 right there. Now, you might ask, is there a way I can improve upon this schedule? Because is this an optimal solution? No, I could do better than this. Does anybody see what I could do to make this better? Well, it's really quite simple. I just move that job that I have sticking on machine 2 over onto machine 3, and boom, we got everything nice and compact there. Notice that the average load of the machines is, in fact, very, very, there's no wiggle room anywhere there. It's compact packing there. So this is an example of an optimal solution. Its Makespan is 3. Okay. So I want to show you, and this is one thing I want you to come out of this talk with, is at least one algorithm that you could show your friends and say, hey, look, that's kind of cool. Or you can even try using it yourself. So I'm going to show you a very basic dispatching rule. In scheduling theory, there's all sorts of examples of dispatching rules. These are very simple rules that you apply to compute schedules or carry out certain tasks. One classic example of one is the so-called list scheduling rule. So its analysis in terms of approximation algorithms was first derived by Ronald Graham in the 1960s. It's often considered one of the earliest examples of approximation algorithms work in the literature. So here's all it is you're going to just schedule the next available task on a machine with least load. It's nice and simple. Notice I don't say anything about the order in which I do it. I'm given a job, and all I have to do is schedule it to a machine with least load. It's really that simple. So when I say load, what do I mean? I mean a machine which has the least amount of stuff it has to process. It's really that simple. So let's do an example, just so we can see one. So I have 5 jobs here. I'm going to just read them from left to right, and I'm just going to place them onto machines, following this list scheduling rule. So all I'm going to do is I'm just going to place job 1 onto machine 1, because that's a machine with least load. I could have picked any one of these, but I'm just going to pick machine 1. Job 2, I'll just stick on machine 2. Job 3, I'll put on machine 3. Now, I want you to take note of the red line I've indicated there on the slide. It's going to change as I execute out this example of applying the list scheduling rule. Now you'll notice that, where should I put job 4? Job 4 should go on machine 1, right? Because notice that the least load is on machine 1. It only has 1 time unit of processing. The other 2 have 2 and 3 respectively. So notice now that job 4 goes there. Why did I pick job 4 to go on machine 1? Remember, every other machine before that point is busy doing something. They're not idling. So I'm going to place it on that machine. That's the reason why I do it. Now notice that because of that, look at the red line, all at that time in my Gantt chart, everywhere to the left of the red line, a machine is processing something. So one note I didn't really say about parallel machines is that as soon as one job finishes, the next one starts immediately. This is going to be an important property for this approximation algorithm to work correctly, or at least when it comes to its analysis. So there's no such thing as a start and end time. I just assume all these jobs can be processed right from the get-go. There's no special order they have to be completed either. However, it's worth noting that you can use this rule even when there isn't ordering on the jobs. You just, like I said, just assign the next available task to a machine with least load. And you actually will get the same theoretic result I'm going to mention in a moment. So just be aware of that fact. So notice there is no idling going on, even after I put job 5 on there. So where we go with this? Well, I just want to make 2 observations for you. I'm not going to do the proof here just for the sake of time, but I want to make 2 observations. The first one is, if you look at the machine that schedules the last job, notice that we put it on there because that machine was a machine with least load. But I could have placed a really long job on that machine that took the last job. That job could take a long time, but it can never take longer than the optimal make span. Why? Because the longest job has to be contained in the schedule itself. So there's no way it could actually possibly be longer than the optimum. Sorry, I'm getting so excited. I'm getting so excited here. The point here is that that's one observation. The other one is, just like in my first example, I want you to think about, could I fit all the jobs on the left side of the red line in that hatched rectangle? In some instances, I will be able to. Other ones, I will not be able to. So let's think about it. What does that red line really represent? Well, that is the point for which every machine is busy before I place the next job. But it also could be a lower bound on the average load of all the machines. Now, like I said, I'm not going to derive this for you, but because of a principle called the averaging principle, this serves as actually a lower bound on the optimum. So if you look at the machine that finishes last, machine 1, for example, this is not a general proof. This is just illustrating the properties. All the time that's going to take up to that point can be no more than the average load up to that point, right? Because all the other ones are busy. That's no more than the optimum. Plus, this last job I dump on there, which is no more than the optimum. Hence, it's going to be no more than twice the value of the optimum. So this is, in fact, a 2 approximation algorithm. So all you would have to do is just take each one of your tasks, you place on a machine with least load, and you can guarantee that the answer you're going to get is no worse than twice the value of the optimum make span. So is that nice? So one other fact that's interesting is Graham also proved, now this is only for this case I'm talking about here. This here, if you actually sort the jobs from longest to shortest, this is called the longest processing time rule. You can actually bring the 2 down to 4/3. So it can become a 4/3 approximation algorithm. So if you sort all the jobs from longest to shortest, you can actually get better answers, which is very interesting in its own right. In fact, you can take this idea and generalize it much further, and you actually end up with a PTAS. But I'm not going to talk about those details here. I just want to get you cozy with the idea of parallel machine scheduling. So I have jobs, I have machines, I need to schedule the jobs onto the machines. And I want to minimize what? The length of the schedule, the make span. So that brings me to talking about unrelated parallel machine scheduling. I'm going to call this Cmax. That is its fancy scheduling theoretic name. Remember, R means unrelated, Cmax means Makespan. Nice and simple. So you might ask, Dan, what's different about this problem as opposed to the one you just showed me? It's actually the third bullet point here I actually have on this slide. So notice here that now, if I have a job and I schedule on a machine, it's going to have a processing time that's Pij as opposed to just Pj. Jobs would have lengths in identical parallel machine scheduling, meaning that if I schedule a job on a machine, it takes that time. It takes the length of that job for this total time. Here, however, its length is actually completely independent of the machine you place it on. It's purely heterogeneous. You can think of it like the processing times are encoded as a matrix or a table. So it's very much more of a general case. So Prj here represents the processing time of a job. I'm going to give you an example of what I mean here. So this is a much more general case than the one I first showed you. So just for the sake of convention, I'm going to show you one other thing. Conventionally, scheduling theorists like to use the symbol infinity to represent that a job is it's going to take too long to get scheduled on that machine, meaning that we just put an infinity there to just forbid a job from getting scheduled on that machine. So if you see infinity in this context, like a table like this or a matrix, just means you can't schedule that job on that machine. Hopefully that's clear. Okay. So, so imagine I have this matrix here. So the rows represent the machines, the columns represent the jobs. And for example, if I try to schedule job 1 on machine 1, it will take 1 time unit. But notice it cannot be placed on any of the other machines because it will take too long. However, job 2 can take 1 time unit on machine 1, 2 time units on machine 2, and 3 time units on machine 3. So you might ask, like, okay, well, what does that mean? It means the job's processing time can grow or shrink, and this depends on the machine, but it is not entirely dependent on the machine. An example where it's only dependent on the machine is the so-called uniform parallel machine case where the machines have speeds. I'll talk about a case like that later. But my point here is that you'll notice that the processing time actually can vary between the machines, and there's no intrinsic relationship the jobs and machines have when it comes to processing time. So just to illustrate here, here's an example of a schedule. So for example, I've scheduled jobs 1 and 2 on machine 1, but you'll notice that now, unlike in the first case, I don't really have a lot of the nice cozy properties I had before, because now a job could take very long if I were to schedule it onto a different machine. For example, I think it's job 4 over there. Yeah, job 4 could take 6 time units on machine 3 versus 1 time unit. That's a big difference, right? So hopefully this gives you a flavor of this classic combinatorial optimization problem. So you might ask, Dan, what has been done with approximation algorithms here? So you said that for identical parallel machine scheduling, you said that there actually are PTASs, right? So for this Cmax case, there are PTASs. But what about for Cmax? Well, the answer is no, they don't exist, assuming P is not equal to NP. So you might ask, well, what's the best we currently have here? So the techniques I showed you earlier, like this so-called, what is called a greedy approach or greedy algorithm, like our list scheduling algorithm or longest processing time. First, these perform poorly when it comes from an approximation algorithm standpoint for Cmax. In fact, you can have an M approximation if you tried using a rule called earliest completion time first. So in that case, what you do is you would always schedule a job onto the machine where the completion time of all the jobs up to that point on that machine is as early as possible. If you use that, you get an M approximation. And remember, M is a part of the problem. So M, you could have many, many machines. There isn't just like 1 or 2 machines. It can be, like I had my picture here, there could exist an instance with like 1,000 machines or 10,000 machines. It has to be able to solve every problem instance in the sense that we're getting a nice approximation. Remember, we're relaxing the rules a little bit. We don't want necessarily, like, it would be nice if we can get an exact approach here, but because this is NP hard and we want efficient algorithms, where it's unlikely we're going to find that. So The interesting result is from 1990 or around 1990 is this paper by Lenstra, Schmois, and Tardos. They developed the first constant factor approximation algorithm for our Cmax, and it's based on an idea called linear programming relaxations plus so-called linear programming rounding, so LP rounding. So I'm just going to give you kind of a sketch of the idea of linear programming rounding or LP rounding. So it boils down to this. So first, what you do is you have a problem formulation, and we use the language of mathematical programming. This isn't like a programming language, so per se. It is a formulation of a type of problem called an integer program. So you're going to create an integer linear program. So you'd formulate one of these. So this is just at the design phase of this. So you'd formulate an integer linear program, and this will tell you how to schedule the jobs onto the machines. The problem is that this problem is actually quite difficult. This is actually NP hard to do. So what we do is we sacrifice the fact it could give us true decisions of yes, schedule that job onto that machine. We instead get what we call an LP relaxation of the integer program. So we end up with an LP relaxation. So here's the idea in an LP rounding approximation algorithm. So we end up with one of these. So I'm going to assume that we have a guess of what the optimal answer is. So imagine I give you a guess and it's like tau or something. I'll explain more of this process later. So I have a guess. I'll call it tau. And what I would like to do is, if there exists a schedule with Makespan tau, I want the algorithm to be able to produce me a feasible solution. But because it's an NP hard problem, I'm going to expect that tau is not going to be what I'm really going to get. Possibly. I might get something actually like 2 times tau or 3 times tau as output from the value of our answer. So what I do is I take and I solve this. So I solve the LP relaxation. So that's usually the first step once you have this. And then you need to round the answer. So you round the answer. So for example, in Lenstra, Schmois, and Tardos' algorithm, what you do is you actually use the properties of your LP relaxation, and it has a very nice special structure that allows you to make a matching argument. So what you use is you compute a matching that introduces an additional load onto the machines, but it actually assigns all the remaining jobs that are only so-called fractionally assigned. Because when you solve this, some of the variables in the so-called integer linear program relaxation, so the relaxation of it, you'll end up with some answers that are going to have telling you, yes, schedule this job on this machine. There's others that are going to be like, oh, well, kinda, it's like halfway there. You need to round these. So this algorithm uses a matching approach to actually compute the final schedule. And then you produce the schedule if you have one. So you produce the schedule. And the nice thing that is great about LP relaxations is because of the nature of the relationship between an integer linear program and an LP relaxation of it, is that if you don't get an answer here, you could reject quite quickly and say there is no answer. That's at least pretty common with a lot of these. There are other steps that might be involved if you really want to get crafty, but this is the general flavor of this approach. I just want to give you an idea so that when I talk about this in a moment, you'll have a flavor of what I mean by it. So the algorithm that's used by Lenstra, Schmois, and Tardos really popularized this technique in the scheduling community. So that brings me to talking a bit about just general flavor of what's been done, what hasn't been done yet. So the best known approximation ratios that exist for this problem on a constant level are 2. So for general M, you might notice that one that says 2 minus 1 over M. Well, remember, M is a part of the problem. So if M can be very, very large, it could approach that 1 over M, so it's basically 0. So it's still a 2 approximation in general. So it's just a slight increase in improvement on the approximation ratio. There's also this other approach by Gehring et al. What they did is they improved the running time by using a flow-based approach as opposed to just one of these types of approaches. It's worth noting that there actually is an improvement on this one. That's by Schmois and Tardos. That's purely combinatorial. So it takes away one aspect of what I just described here. One facet I didn't describe to you is that actually you have to compute a so-called basic feasible solution for this guy right here. And it has a very special property that the second step uses. What this result that I don't have listed here, but Schmoyes and Tardos, they show you how you get an answer from a solution so that you can make it look like a basic feasible solution. But it's done in a different way. But the general flavor of it is basically the same idea. Anyways, that's the good news, is that there are two approximation algorithms for this problem. The bad news is that you might ask, well, how much better can we do? This is the other side of the approximation algorithms research that people study. It's how good can the approximation ratio be, assuming that p is not equal to np. So, unfortunately, we don't know the result of p versus np, but right now, you might ask, okay, well, assuming that it is the fact that p is not equal to np, what's the best possible approach or best possible approximation factor or ratio that we can get? And Lancia, Schmoyes, and Tardos, they gave us that answer, or at least currently the best known one. We don't know if there actually is a better lower bound on the approximation ratio at this point, but the best known one is 3/2. So if you're able to come up with an approximation algorithm where the approximation ratio is less than 1.5, then you would be able to prove that p is equal to np. The way you would do that is you would actually come up with an algorithm that solves the so-called three-dimensional matching problem, one of these NP-complete problems. So this leads you to a problem where now we have a 3/2 to 2 gap. And the theory has not really prescribed what exactly the reason why this is. We don't actually have a proof for closing this gap. So this is often considered one of the most challenging open problems in approximation algorithms today, is reconciling this little 0.5 gap. Because currently, the theory we have, it's mostly speculative. We still have we don't have definitive answers, but we have a lot of ideas ranging from mathematical programming ideas to certain special cases that are being studied. And I'm going to focus mostly on the latter in this talk. So let me navigate through this. So like I said, this is a very intensely studied problem. So there's no way I can cram everything that researchers have been studying into this talk. Instead, what I'm going to do is I'm going to just kind of navigate through some of the interesting cases that have been looked at in recent years, and some of the ones that I've been particularly interested in. And I'll describe a couple of examples of new results that have been established and some of my own. So just I want to give a flavor of what's currently being done with respect to unrelated parallel machine scheduling when it comes to approximation algorithms. So a lot of the time people have been looking at this from a special case study. So what we would like to know is what intrinsic properties about unrelated parallel machine scheduling problems makes Cmax much harder to approximate. So a lot of theoreticians, for example, like myself, believe it's mostly the heterogeneous nature of the job. So one common characteristic that this takes on is so-called eligibility of jobs on machines. So notice how I had like infinities that were in my matrix or table? What if those are purely arbitrary? That seems kind of like having these jobs that could be basically placed on any one of the machines. It's heterogeneous. That's one speculation of why things are pretty tough. So let me talk a little bit about just the flavor for which we could talk about these things. So I'll talk about the so-called restricted assignment problem in a moment. But I just want to give you a flavor of some other things that people have been looking at before I specialize a little further. So the first thing is that there's so-called structural properties that people have been looking at with respect to Cmax. So I'm going to give you a couple of quick examples of this, but I'm not going to go into too much detail. So if you're curious about this, just let me know in the comments, okay? So when it comes to structural properties, people have been studying, for example, the processing time matrix. So remember I told you it's like a table or a matrix? Naturally, people look at the matrix and they want to study parts of or properties of said matrix. For example, some people have been studying the rank of the matrix. So if you consider ranks of certain values, what exactly happens? Another good example, and this is one I'm going to touch on later, is, for example, studying something called a machine type. There's also other types called job types. So these are just a couple of examples. A third one that actually I find interesting, and this is one that I've done actually work on in collaboration with a couple other researchers, is so-called simple intersection structures. So just to kind of walk back here, I just want to give you an example of what I mean. So one way you can represent the instances of our Cmax is using something called a job intersection graph. And the way it works is as follows, is that you have your jobs. So you have n jobs, right? And each one of these can be represented in a network or graph, where each one of the jobs is going to be representing a vertex in this graph. And the structure is going to work as follows: is if if any two job can be placed onto the same machine, we connect an edge between them. So for example, if there exists a machine that could schedule, for example, job 1 or job 2 or both, then we put an edge between them. Likewise, if job 2 and job 3 and job 2 all could be placed on machine 1, then I would form a triangle. There might also be other machines that they might have in common, so-called they share a common machine. Hence the intersection name in the job intersection graph. So people like myself have looked at cases like this. So you could study so-called machine intersection graphs as well. That also has been studied. But one positive result that's actually kind of neat about job intersection graphs is if you consider our Cmax and you specialize it for only certain kinds of job intersection graphs. So for example, if the graph doesn't contain so-called triangles, so this is an example of a triangle. If your graph doesn't contain these, there actually does exist a polynomial time algorithm to solve any instance of our Cmax that has such structure. And in fact, it's very easy to detect if a graph like this has triangles in it. So you could almost see this like a little bootstrap method. What you would do is you would check if you'd build one of these graphs from your instance. You test if the graph is triangle free. If it's triangle free, then you could actually solve it in polynomial time. It uses a flow-based algorithm. So it's worth noting that it's also rather pessimistic results as well when it comes to this work. For example, if the job intersection graph is planar, so if you're considering all the instances, and you want to say, okay, if the job intersection graph is planar, how good can we approximate our results? The answer is unfortunately quite pessimistic. That 3/2 lower bound that I talked about just before, that also persists here as well. There's all sorts of cases. If you're curious about the paper, I could always give you it or send it to you. But we published it. It was published in Theoretical Computer Science in 2020. But there's a lot of work. This isn't even all of it, but this is some of it. I just want to give you a flavor of what I mean by structural properties. All of the things technically I'm talking about are all structural properties, just they're of a very special kind that have been intensely studied. So I'm mostly going to be highlighting some of these. Thirdly, I'm going to be highlighting one more special case at the end of this section of the talk. So I'm going to talk about first the restricted assignment problem. So this is a very interesting special case for one reason. Is I talked earlier about this idea that some jobs can be eligible to be placed on certain machines. So naturally, was there a simple way for me to capture that? Well, remember the first problem I showed you? Cmax, identical parallel machine scheduling. So we have Makespan Minimization, identical parallel machines. Well, we had PTASs there, right? Maybe if we add this eligibility nature to it, maybe we might find something interesting. And keep in mind, we're still talking about a problem that very much could have killer applications in all sorts of different settings. So it's not like we're not talking about something that isn't actually a tangible thing you could actually use. We're talking about something very real. All we're going to do is the following. And it's going to be sound like a very simple wrinkle we're going to add to this problem. What we're going to do is each job is going to have a length, just like in PCmax, except there's going to be a set of machines that job can only be processed on. So its processing times are either going to be PJ, the length of the job, or infinity, meaning you can't place that job on that machine. So the set of machines it can be processed on are so-called processing sets. So here's just a quick example. So notice that I have in my matrix here, I have job 1. Notice that the job only takes 2 time units on any machine it can be scheduled on. But notice it can't be scheduled on machine 1. That's just the general flavor of this problem. So you can so the way I like to think about it is imagine you have a bunch of workers and you have a bunch of tasks they need to complete in the day. And say Billy or Sally can't accomplish a certain task that another one of your staff or people in your project can do. The eligibility constraints naturally classify that, right? Is that there's some tasks that some of your workers can do, other ones they can't do. So the good news / bad news is that there are 2 approximation algorithms for this problem. However, the same ones for our Cmax. Those are the best you currently have with polynomial time. It also still has the same 3/2 lower bound from our Cmax we talked about previously. In fact, the 3/2 that I talked about earlier, it actually is derived from this special case. So if you're wondering, oh yeah, is it any special, like there's some special thing? No, actually the 3/2 lower bound I talked about before with the 3-dimensional matching, it actually comes from this problem. That's why it's interesting. But now you might ask, well, what makes this one a little different? Is that actually there has been some progress recently, in the last half decade at least, on trying to improve the approximation ratio from 2 steps, 2 kind of prongs. The first one is so-called estimation. So people have been looking at how you can estimate the optimal schedules, but not necessarily construct them. This derives from a result from Ole Svensson from the late 2000s, where Svensson had proven that you can actually do better than 2 for the approximation ratio. However, their algorithm we don't necessarily know if it runs actually in polynomial time. It doesn't seem to, but it's very unclear. It's been quite a while since I've looked at that algorithm, by the way. The point here is that it can correctly estimate answers less than twice as bad. So it could give you the number, like the value, like algae. It could give you this, but it can't actually give you the schedule. A lot of the theory around this is built around the so-called configuration linear program. It's a very structured program. It's a very strong one. But so that's one prong. There has been successful work with respect to when they have 2 job lengths. For example, if you have a small job length and a big job length. So for example, if my matrix only had 2 numbers in it other than infinity. So a small length, big length. So a job either could take a little time or a big amount of time. Or it just can't be scheduled on a machine. In cases like this, there do exist estimations. I believe it's like 5/3 plus a little epsilon. I think that's currently the best we currently have when it comes to that. That was developed by a colleague of mine. Well, colleagues, to be technical. But also, there have been some positive results with respect to estimation for restricted assignment problem in general. The best known estimation algorithms do actually exist. Is 11/6 plus a little epsilon. So it's like 1.8334 is currently the best known way you can approximate a something such as a restricted assignment problem in this so-called estimation sense. However, the neat thing about that result, this is from Jensen and Rowetter from 2017 at IPCO. They've shown that if you actually don't just use polynomial time, but you use quasi-polynomial time. So this is an example of a sub-exponential time as opposed to polynomial. This is something in between polynomial and exponential time. You can actually build schedules where their makespan is no worse than 11/6 plus epsilon times the optimum. So you can actually build the schedules. It isn't just about estimating the answers. Actually, you build the schedule. But it requires quasi-polynomial time. So the question really becomes, can we actually get that in polynomial time? We don't know right now. And I'm actually quite excited about that. So other than that, it's worth noting that we have very few examples of special cases where we actually can break the 2 barrier. So we know the best known approximation algorithm ratio here is 2. can we break the 2 barrier? That's really one ultimate question that a lot of people have been curious about. So for restricted assignment, in general, it's still 2, but something could change in the future. I'm not quite sure. We don't know yet. When it comes to only 2 lengths, like a small length and big length, there has been some positive work using local search algorithms, where I believe there is a result that came out not that long ago that actually does have an approximation ratio better than 2. So it's still like 1.89, I think, 88 or something, 89, something like that. It's pretty close to 1.9. But there has been positive developments. Now I'm going to address the next row of my chart here. And I just want to highlight 2 things. So first, I already talked about 2-length restricted assignment already. I want to mention that there's this so-called case called parallel machine scheduling with processing set restrictions. This is a special case where you notice how my eligibility constraint, my processing sets, they're completely arbitrary in the restricted assignment problem. What if they actually have more structure to them? For example, imagine all my jobs were associated with a given machine and I impose some graph theoretic structure on them. For example, a tree or a directed chain, something like that. I'll talk about this towards the end of this talk. But in these cases, there actually are positive results. For certain cases, there's actually PTASs, which is quite exciting. But I'll talk a little bit about that towards the end of this talk. I have something in relation to this I want to discuss. Instead, I'm going to highlight something called the graph balancing problem. So this is a problem I've been fascinated with for a number of years now. And it's really just a special case of the restricted assignment problem. So, like I said, I believe that eligibility constraints play a very big role in how difficult our approximation problem, like one of these problems where we want a better approximation algorithm, sits. So naturally, this is like you can think of this as the most elegant or simplest version of this. And it's quite natural. So all we're going to do is we're going to assume that each one of the jobs can be processed on one of at most 2 possible machines. Now, for anybody that's watching this and knows a thing or 2 about matrices, or think of it like the table, if you have at most 2 entries per column, you actually could be representing a graph using this. In fact, a weighted multigraph. So I'll let you think about how that's done, but the point here is that you could represent the input instance, or our jobs and machines, as vertices and edges, where the vertices are machines and the edges are jobs. So here's just an example of what I mean. So notice I have 3 machines here, and I have 1, 2, 3, 4 jobs. Each one's an edge, and the number represents the length of that job. So like I said, it's a special case of restricted assignment. It only has a length, but it only can be scheduled on certain machines. The way we characterize that is by directing or orienting an edge towards one of its at most 2 possible endpoints. So, for example, the edge there with weight 2. So you notice that line there with 2 there. You know what I'm talking about. It's about generally over here somewhere over here. The one with the number 2 on it. That could either be directed towards job machine 1 or machine 2. By directing it towards that vertex or placing that job on that machine, you're introducing a load of 2 to that machine. So there's a correspondence between directing edges or orienting edges in this graph versus assigning a job to a machine. So when we talk about makespan in a schedule, it's identical to talking about the maximal load of a vertex. So the load is just simply the sum of all the edge weights of edges directed towards a vertex. So just to give an example here. So this is the same graph I had from before. So notice if I direct 2 edges that are incident on machine 1 towards machine 1, I get a load of 3 on there. I have a self-loop off of machine 2, so it contributes a load of 3 there. And lastly, I have an edge that I could direct towards machine 3, introduces a load of 3. This is an example of an optimal orientation or optimal schedule. Its optimal makespan is 3. So I have some good news for this case. First thing, there actually is a better than 2 approximation algorithm here. This is one of those small number of examples. The beautiful thing that this algorithm does is actually based on a similar idea I just talked about earlier. So I want to just remind you of the overall idea, and I'll kind of tell you what the wrinkle is. I'm not going to go into too many details here, but it's based on LP rounding. So you have an LP relaxation, you solve it, and then you're going to round it. Now, because of the graph theoretic nature of this problem, and the way you could specialize the integer program when we get a relaxation, it has some nice properties. When you actually solve instances of this linear program, what happens is you end up with a structure that ends up looking like this. Say you have edges that aren't entirely directed towards one of the two endpoints. These take on the structure of the following. They may look like a tree, they may look like a cycle attached to a tree, or it just might look like a cycle. And the way you perform the rounding is using a threshold. So this is just a number that I use to determine to do one of two things. So if ever I encounter a cycle, if there exists a cycle, what I do is I use a flow-based approach of pushing the fractional amounts around the cycle to eliminate a cycle, and then I end up with trees that I can direct away from or towards a root. So the way you do this is you direct an edge towards a leaf or away from a leaf. So this is using a threshold. So if the amount that is oriented towards the vertex is larger than the threshold, you're going to do one thing, or you're going to do the other thing. So you'll either direct an edge towards a vertex, or you'll direct it away from the vertex, directing it, passing it through an entire tree, performing a rounding. So that's how the rounding works. It's quite elegant, but the big point I want to get at is it uses a threshold-based approach based on graph theoretic structures. So it's quite elegant. So that's the good news. So that's from Ibelender et al. I'll refer to that in a moment. But it also has a 3/2 lower bound. So the same authors I just mentioned, they also prove that you can actually do no better than 3/2 unless p is equal to np. Here they actually showed it also is true when you only have one of two possible job lengths. So you can have a big job length and a small job length, just like what I was talking about earlier. So you can think of it as a heavy edge versus a light edge, or a big job length, small job length. Now, this is one of the interesting developments that's come out not that long ago, is that Page and Solis-Oba, they had proven that there exists 3/2 approximation algorithms for graph balancing when you have two job lengths. So this is a very interesting kind of breakthrough when it comes to this problem, because this closes the gap on graph balancing with two job lengths. So that problem from an approximation standpoint is resolved. The only thing you can really do at that point, assuming p is not equal to np, is coming up with more efficient algorithms. The interesting fact about this is that actually independently there were two other groups that also came up with other techniques to derive 3/2 approximation algorithms for the same problem. One uses a local search-based approach, the other one uses a flow-based approach. So if you're curious more about those, I can let you know in the comments if you ask about it. Actually, in 2019, in my dissertation, I do give a flow-based approach. It's really, really nice. It reduces most things to max flow. I would consider it a much better algorithm than the one I came up with my PhD supervisor in 2016. It's very elegant. So it's a nice use of flows. So that being said, we know that the 3/2 gap, it's completely gone. And it's worth noting that this 3/2 was an improvement on like 1.652 that was established in like 2012 or something like that. It was around that time, 2012, 2013. So we had shown how to tighten that up a little bit. So the natural question is, if we have that resolved, can we generalize graph balancing with two job lengths to a tougher case? And this is where the idea of talking about uniform parallel machines really comes from, for us. So remember, uniform parallel machines is just a machine environment. It's a very well-studied problem in its own right. We're going to look at graph balancing with respect to it. So we're going to look at graph balancing with two job lengths and two machine speeds. What did the speeds do? So remember I said there's a small job length and a big job length, and you have a slow speed and a fast speed. So each machine has a speed, and it causes a application of the job to either get longer or shorter depending on that speed. So if a job has length pj and the machine has a speed si, the processing time is going to be Pj over Si. So it's relative to the machine speed, so it alters how long the job is going to take. Now, the thing that's very exciting here is actually, this came out, we got this published in 2019 in the Journal of Combinatorial Optimization, is that you actually can derive a better than 2 approximation algorithm here. It ends up having a very strange approximation ratio. It's square root of 65 plus 7 over 8. It's about 1.882. So that's better than 2, and the thing that makes this interesting is the technique we use. So we use the approach by Ibelander et al. With this thresholding idea. So what we do is we build a much more general structure than the one that they do by trying to encode the machine speed somewhere into the graph by knocking out some particular cases. It's a rather complicated algorithm in some respects, mostly due to its analysis. But what we do is we try to get that graph theoretic structure like is used in that algorithm. But what we do is instead of having a single threshold that determines which way we should direct edges, the fractionally oriented edges, we use multiple thresholds depending on conditions about the machine speeds. So in our analysis, we use a very clever argument to actually get a relationship between the machine speeds and the amount of load that increases. So using that information, we actually figure out what case and what threshold should be. So it's a neat analysis, but it's rather complicated. So in this case, there actually is a better than 2 approximation. It's constructive. There's no estimation stuff going on here. It's purely constructive. Now, what makes this result interesting is, like I said, there's very few examples. There's maybe, the number of them is at most on both of my hands tops that do exist of cases where we actually have better than 2 approximations, where we still have a special case where this lower bound of 3/2 persists for unrelated parallel machine scheduling. So what makes this special case interesting is that this is, to my best of my knowledge, is the first special case of our Cmax that has been studied where we have different machine speeds where we actually have a better than 2 approximation of that problem, where it still has this 3/2 lower bound for the problem. So that's what makes this result really exciting. So an open problem actually I do have is, can we improve on this approximation ratio for this problem? It's currently unknown. I'm not aware of any theoretic reason why you cannot do any better than this. I think it might actually be able to be improved upon. It's not quite clear if whether the ideas we have could be built upon or we need a stronger tool. So that wraps up the third part of this talk. The last part of this talk, I'm going to focus on a paper that we published. I published with Roberto Solosoba on bag constraints. So we're going to look at a generalization of Makespan minimization on unrelated parallel machines. We're going to introduce a very basic model of fault tolerant scheduling or system stable scheduling. So it's going to work like the following. So I'm going to denote this as our bag Cmax, where bag is the job characteristic that denotes the bag constraint. I'm going to define that in one moment. And we're going to assume the following. That I'm going to have bags. So these are going to be a fancy name for sets, where I'm going to have B of them. So I'm going to have B sets. And what's going to happen is I'm going to make sure that all the jobs are distributed into these sets, called bags. So this is going to partition the set of jobs into bags. And the bag constraint tells me, and this is what I have to satisfy, is that no 2 jobs from the same bag can be placed onto the same machine at any time during the execution of the schedule. So that's what the bag constraint says. So just to illustrate this, I have an example here where I have 2 bags and I have 4 jobs. Just for the sake of time, I just have a table here and I have my bags denoted here where I have job 1 and job 4 in bag 1 and job 2 and job 3 in bag 2. I want you to notice that I have, if I were to do this without bag constraints imposed, I would naturally put job 1 and job 4 on machine 1, job 2 and job 3 on machine 2. But you can't do that here. Why? Because that would violate the bag constraint, right? So what do? Well, you'd have job 4 or job 1 has to take the 3 time units. Otherwise, we're going to violate the bag constraints. So we're going to have to push around job 2 and job 3 and job 1 and job 4. And we're going to end up with an optimal schedule where it has Makespan 4. Okay? So this bag constraint actually does change the behavior of the problem a little bit. It's a generalization because if you let the number of bags be equal to the number of jobs, so if you let B equal N, that means that each job is going to have to be in its own bag. And if there's only one job per bag, there's no way no two jobs could even conflict with one another. So that's why this is a general case of that problem. So naturally you might ask, Dan, why would we want to study a problem like this? Well, like I said, and this is what I alluded to, is imagine you have a bunch of critical tasks that you need to make sure that they are safely operating on a complex system. What you could do is you could place them all into a bag along with your typical tasks that could belong in their own bags, or they might be paired together. I'm not quite sure. This would be up to the person that's using the algorithm. What they would do is they would like to be able to spread these critical tasks to as many of the machines as possible, so that if one of the machines were to fail, all of the critical tasks would be able to still execute on all the other machines. So if one machine fails, all your other critical tasks are going to still be able to run. So one way you could think about this is, imagine you have one critical task, you need to make sure it runs on at least one of the machines, but you know that there is a prone possibility that one of the machines might fail. Then this will guarantee you that if one of them fails, at least the other machines are going to be able to run at least once this critical task. Okay? So you can think of this like a simple way we could talk about system stability, and you could think of it like a simple model for fault tolerance. That's why I find it interesting. So you might think of an example like a large aircraft, where you might want to have it where you actually want to have a complex system where you have, say machines, so software-based operations of temperature control for your engines, for example. You may have communications on the plane. You may have several moving parts of your plane. And planes are rather complicated pieces of technology, which means they are prone to failure if they are not designed carefully. Because aircrafts need to be designed to be safe. That is something very important about planes and the technology around planes. Failure is not deemed acceptable on an aircraft. There's many things that could go wrong. So what you might have is you might have something like this in mind if you have the controls of your aircraft attached to something like the temperature control of the aircraft. So naturally, a lot of aircraft, they have jet engines sufficient to be able to keep the aircraft in the air if, say, one of the two engines on the wing, say, were to fail. Not necessarily every airplane has this property, but many that have jet engines will be capable of such things if they go fast enough. I'm not sure, it would depend on the model, but my point is that in a big complex system, whether it be software on an aircraft or on your computer or on a network, you would not want to have it where you have all your important tasks all clustered on one machine. You'd want to spread them across to as many machines as you can. That's the general idea here. So that's why I find this interesting. So that's at least one of the main reasons why you might study this problem. This brings me to talking about a natural parameter to study this problem, a structural property. It's so-called machine types. So we're going to study these in relation to the bag constraints for this section. So I'm going to define two machines that have the same machine type if you look at the rows and you see the entries in the rows are the exact same. So if they're the exact same, we say they are the same machine type. Sorry, I'm getting really excited here. So just in my example here, notice that the first two rows are the exact same. So I say those are machine type 1. However, the third row is different, so I'm just going to call that a type 2 machine. So this is an example where I have two machine types. So a natural way you could think about machine types, and this is a very realistic and natural thing you can actually think about in a real parallel environment, is I'm going to denote the number of machine types as delta. And if you think about it, this should sound like a bunch of homogeneous processors formed into clusters. So if delta, for example, were 4, I can have 4 machine clusters like in my picture here. And this is something quite natural to occur in practice, where you might have clusters, where each cluster is a homogeneous, like all of them are homogeneous amongst each other, but they're networked typically together. So here's an example. So it doesn't necessarily have to be that they're physically connected to each other. The point is that they can represent clusters of processors. And so it's very general. But it's also a natural parameter to study because if delta varies, you actually get different machine environments like the ones I was mentioning over here. So like these guys over here. If delta is equal to 1, you get identical parallel machine scheduling. When delta is equal to the number of machine speeds, you get the uniform parallel machine case. And when you have delta is at most m, you get the unrelated parallel machine case. So it has that whole continuum of machine environments encoded into this parameter. That's what makes it interesting, at least from my standpoint. So I'm going to show you just a general gist of idea of how we can design a PTAS for unrelated parallel machine scheduling when we have bag constraints in place under two conditions. One, that we assume the number of machine types is constant, and two, that the number of bags is constant. So I'm going to assume that those two parameters are constants. So the first step in my algorithm is I'm going to compute a B approximate value that captures this bound I have on the screen. You can design such an algorithm using network flows. So next what I do is I use binary search. Now, I said I was going to talk a little bit about this, but this is a very powerful technique that people do use very often when we study optimization problems. What we want to cast them as decision problems is, imagine I give you some guess. And I tell you, okay, does there exist a schedule of length tau, for example? Either it exists or it doesn't, right? So you can answer yes, no questions about this. And we can play a little game. And you could naturally say, okay, yes, there is a schedule, or no, there isn't. You might know this as a game, like hot, too cold. So you might ask, am I warm or am I cold? Or you might play guess a number. And somebody might give you a number to guess, and you have to guess, and they tell you higher or lower. That's the exact same game you're going to be playing here. That's what binary search does. Now, the thing that makes this a little different is that we're dealing with an NP-hard problem, so we can't just simply say yes or no. We need to say maybe, as in there exists a schedule, but there might exist a better one. And no, meaning definitively there is no schedule with that length tau. So that's what we're going to be adopting, and that's what I mean by use binary search over that interval. So you're going to play a guessing game. You're going to start in the middle of that interval, and you're going to just simply try to play, is the number too big or too small? But you're going to have it either maybe it might be this, but it might be smaller, or it's going to be that no, your number is just, it's too small. Okay? So the first idea that you might leap to, if you're thinking, okay, the most crudest thing I could cook together to design a PTAS. Well, one thing I can do is take the exact approach. I could exhaust all possible schedules. So that means I'm just going to enumerate all of them. So I just simply imagine I have tau as my guess. And I'm just going to simply try to assign each machine to I'm going to give a bunch of jobs to a machine such that I don't violate the bag constraint. So if I try doing this, there's an exponential number of these, which isn't good. That takes exponential time. We want something that runs in polynomial time. So I'm going to show you how you can take and exhaust all the possible schedules, but I'm going to be able to do it in polynomial time on top of this guessing game. So I'm just going to give you the flavor of it. I'm not going to go into too many details. So we're going to use this bucketing approach. So this is a technical, it's a fancy term that people that design PTASs would tell you. It's the bucketing idea. It's like, so the idea is quite simple. We're going to simplify our instances. So then we're going to look at those simplified instances and see what we can do with them. So what I'm going to do is I'm going to take my Gantt chart. I'm going to break it into increments of tau epsilon over b squared. I break it into these increments. And what I'm going to do is I'm going to try to fit jobs into slots of increments of tau epsilon over b squared. And I'm going to encode this as something called a load configuration for a given machine. So what does that mean? I'm going to give you a vector. It's going to have b components or b positions in it. And the numbers are going to take on the value either from 0 up to b squared over epsilon rounded up. You might ask why? And why are there b components? It's because there's a very important observation. It's because if I want to schedule a job onto a machine, I can't place two jobs from the same bag on the same machine. So you got to think about it like each machine having B representatives at most, where each representative is one from each bag. So it's either you're going to place one from a bag or you're not. But you can't place more than one, right? Otherwise you're going to violate the bag constraints, right? So all we do is I'm going to encode the increments of tau epsilon over b squared that are going to fit my job in there as a number. And that's what the load configuration is. So that's just the general gist of it. The way I like to think about it is that we want to make sure it fits, but it doesn't overfit, as in there's too much wiggle room. This actually comes into play with our proof of how we bound the optimum in a very special way. So we need to make sure it isn't getting too big or too small. So if it's too big, it won't fit. If it's too small, there's going to be too much wiggle. The way I like to think about it is like a shoebox. So naturally, if you have shoes, you get them in shoe boxes very often. Now a shoe like this can fit into the shoebox no problems. When I close it, I can shake it around. There's not too much wiggle in here, right? However, imagine if this shoe was like half this size. You definitely could tell it would wiggle. It might damage the shoe. So we would not want to do that when we design the shoebox. The same idea here. I don't want to design a schedule where the job is definitely going to be too small, meaning that I might end up with a schedule where there's going to be huge gaps that are sitting inside of my schedule. I want to keep everything nice and compact, like a carton of eggs, or a nice shoebox. So just to illustrate what I mean by these numbers, just in case it's not clear, here's just an example here. Notice that I have each representative from a bag, and I've represented them as numbers, and those are my increments of those. So remember, this inequality here is just to satisfy a so-called valid machine load configuration here. So we'll have an algorithm that actually determines if that's valid or not. We encode this into a network. But the big observation here is that each one of these positions, let me move over here, is that each one of the positions, it could be 0, it could be 1, it could be 2, it could be anything up to, it could be at most, what was the number again? What was that number? It was b squared over epsilon. I think I misspoke earlier. I think I said tau epsilon. It's b squared over epsilon. It's important that we don't have it so it's too big. It comes up in the algebra when you're doing the analysis. So let me just go back over here. So we have increments all like this. So each one of the positions, so we have b positions. Each one can be 0 up to this number. So each one of them can have these, and it's all purely independent. So if I have b spots, so I can put one of these numbers, how many possible elements can I place into each one? Well, it's this number plus 1, because the 0 can also be included. What does that mean? The total number of load configurations possible is at most 1 plus the ceiling of b squared over epsilon, raised to how many positions there are in a load configuration, which is b, because there's b positions. But I told you that b is a constant, right? So you're going to end up with something that's like, okay, 1 plus some constant over epsilon raised to another constant. So notice that with respect to epsilon, if epsilon is fixed, this is all going to end up being a constant, right? Isn't that nice? So let's go back over here. So I'm just going to call that D. And now I haven't told you exact, so keep in mind, because of that fact, I can enumerate all possible load configurations. So I can just select them. And if I select one, then I can use that and I can assign the jobs. So I have some representation of the loads for a given machine. I can index into it because I can list them all. And there's some constant number of them for a fixed epsilon. I need to actually encode the schedule, so I need to enumerate all possible schedules. So this is the way I'm going to represent it. I'm going to use another vector. It's going to have delta times d many positions in it. The easy way I like to think about it more is as rows. So there's d positions along each row, but there's delta many rows. Sorry, so what's going to happen is I'm going to have each position represent the number of machines of a given type that are going to be assigned a given load configuration. if I try to enumerate all possible ones of these, I end up actually with a polynomial number. It's big O of m to the delta times d. And delta and d for a fixed epsilon are going to end up being constant. So that's very nice, right? So it means that I can actually enumerate all possible schedule configurations. There are going to be some that are actually going to be junk, and I will never want to use them. Other ones are going to be valid. So what my algorithm is going to do is I'm going to, for my guess, I'm going to compute all valid schedule configurations. And then I'm going to then choose one where all the jobs can be allocated to the machines. And because I try them all, I know for a fact I'm going to end up with one that's going to look nice. But how nice? Well, in the proof, we show that you can get as close to 1 plus epsilon times the optimum. Hence, it's a PTAS. So we end up with a PTAS for this case. As an interesting result, because of the parameter of the machine types, if you know your machine types is going to end up being the number of machine speeds, like we're looking at a uniform parallel machine case, you end up actually getting another PTAS there, but we have to assume that the number of bags is constant and the number of machine speeds is constant. One fact I don't think I kind of glossed over is the fact that it isn't necessarily that it's just purely identical. It's that, remember, eligibility constraints they can be encoded here, right? So I just want to make that remark. So I want to wrap up this talk with just some open problems just to think about. So I've already mentioned one, but I'll mention some other ones here. These are involving the bag constraints. So the first one is that we do not know if there's a PTAS for uniform parallel machine scheduling so keep in mind, I'm not even talking about eligibility constraints or anything here. I'm just saying, given the first problem I showed you during this talk, the identical parallel machine scheduling, Makespan minimization, the one where I did list scheduling, if I introduce machine speeds to my machines, and then what I do is I tack on, which by the way, that has a PTAS still. If I introduce the bag constraints, is there a PTAS? Not that long ago, it was established there actually is a PTAS for identical parallel machines with bag constraints. So that was established by Dawson Weiss first in 2017, but there has been one that came out with an efficient PTAS at SPA 2019. So that was developed by some colleagues. So it's not really clear if it's possible for uniform machines. I have spoken to some of my colleagues. I know that there is the belief that it probably does exist. If it does, it might be really ugly. It's not quite clear at this time. We don't know. Number two, can we eliminate the number of bags as a constraint in a PTAS for this problem? Remember, I required the number of machine types and the number of bags to be constant. It's not clear if we can get rid of the number of bags as a constraint on our PTASs. So does there exist a PTAS without that? We know that without bag constraints, it does exist. Colleagues of mine actually did develop an ePTAS in that case, an efficient PTAS. So we can ask kind of similar questions to the ones I had before. Likewise, you'll notice that the degree of the polynomial in my PTAS that I presented to you from the work that we had done, the degree of the polynomial can be very large. Is there a much more efficient PTAS that exists? That is also unknown at this time. One that I'm actually especially interested in, this is one I've been thinking about for some time, is for the graph balancing problem. If we impose the bag constraints, do there exist constant factor approximation algorithms? That's an outstanding problem that I'm very interested in. In the paper I had highlighted earlier, we had shown that there's a B over 2 approximation algorithm, which actually does solve the graph balancing problem with 2 bags polynomially. So it's polynomial time solvable with 2 bags. But when you hit 3 bags, you get that 3 has lower bound pop-up. We don't know if there exists a constant factor approximation algorithm. It could be 8, it could be 16, it could be 32, it could be 100. I don't know. The point is we don't know if it exists or not. I'm very curious about that. And finally, this is one that I'm probably the most interested in, beyond graph balancing with bags, is this process set restriction case I mentioned earlier. Now, here's just to illustrate an example of one such of these. This is an example of an entry I have here on the screen. So Notice that I have all my jobs. I'm going to arrange them into this in tree where each job is going to be associated with a machine. Each machine is going to be representing a vertex in this in tree. So each machine is a vertex in the in tree, and they're directed towards the root of the tree. So what I would like to do is I want to know more structure about the eligibility constraints, the processing sets. The way the tree here is organized is that each job is associated with a machine, and that means that each job can be scheduled on the associated machine or any machine along the path from that machine to the root of the tree. For example, the job here I have associated with machine 3, I'm just trying to see it over here. Yeah, job 3 over there. It's associated with machine 3. It can be scheduled on machine 3 or the root. So this is the example of tree hierarchical processing sets. This is an interesting case. Another one is the so-called grade of service or inclusive processing set case. This is where instead of having an in tree, you have a directed chain. So you have just a chain. That's also a very interesting case. For both of these cases, we know that there actually are PTASs in the classic situation for identical parallel machine scheduling. So if we have identical parallel machines where we introduce processing sets, like our restricted assignment problem, remember, we're talking about when we have more specialized structure for the processing sets that are encoded by structures like this. What we're going to do is, I want to know if there exists PTASs or not, or do there exist constant factor approximation algorithms? I don't know. For the classic situation without bag constraints, they do exist for both of the cases I just described. For the inclusive or grade of service case, or for the tree hierarchical case. Now you might ask, Dan, why is this very important? It's because a lot of problems actually do have structures like this. For example, if I just have a directed chain, you might have jobs that represent tasks that are done for clients. And the rank for which those clients are had, or their priority, is actually the placement it has on the chain. This could be as simple as a bunch of cranes on a dock loading crates onto boats. It could be many different applications. The question is, when you impose the bag constraints, do there exist constant factor approximation algorithms? That is presently unknown, and I'm very interested in that problem. So I'm interested in the inclusive case and this tree hierarchical case. Sorry, I'm getting really excited here. But yeah, this is an outstanding problem that I'm currently working on as well. So that being said, this wraps up all I really have to say at this time. I want to say thank you very much, and have yourself a beautiful day. I'll see you later.